Hey everyone, I wanted to just finish showing you the examples that were in lesson 2.5 that we started to go over in class on Friday, October 9th. So this is the slide that follows this SO2 and PI3 slide that we finished up working with in class. So these snips, these little pictures are taken from actual AP free response questions. So sometimes what they'll do is they'll give you the skeleton structure of the molecule. So you don't have to worry about how to arrange the atoms. You have to just place the bonds and the lone pairs in the appropriate places. So this one on the left, we're gonna start the same thing. We have to count our valence electrons. So we have 2 chlorines that are each halogens with 7 valence electrons. And we have 2 sulfurs that each have 6 valence electrons. So when we're done with this diagram, we need to have a total of 26 electrons showing. So the first thing we do is we start by putting single bonds between the atoms, because this one's different than the ones we've been looking at. There's no like one central atom. So we just start by connecting. So those 3 bonds are equivalent to 6 electrons. So we have 20 left to go in our picture. Now we're going to start with the outside atoms and then work our way in. So each chlorine, the chlorine on the left right now only has 2 valence electrons. So it needs to have 6 more. So that's 6 taken care of. So there's 14 left. Now the chlorine on the right also needs to have 6 more. So take those 6 away and there's 8 more left. Now we have the 2 sulfurs. So the sulfur on the left-hand side here has 2 bonds, right? So that's 4 electrons. So it would need to have 4 more electrons to complete its octet. Okay, so it would have 2 lone pairs, right, or 4 electrons. So there's 4 left. And then our second sulfur also has 2 bonds, so that's 4 electrons. And then we would need to put 2 lone pairs / 4 electrons on that. And that takes care of all of our electrons. Then you double check the chlorine that's on the left, 2, 4, 6, 8, because that bond counts for it. The first sulfur, 2, 4, 6, 8, those bonds count for it. The second sulfur, 2, 4, 6, 8. And then that final chlorine, 2, 4, 6, 8. And if I count up my bonds and my dots, I get 26 electrons. Okay, now this compound on the right, we're going to do our counting. So we have hydrogen, oxygen, and nitrogen. We have 1 hydrogen, so that's 1 valence electron. We have 2 oxygens with 6 valence electrons apiece, and we have 1 nitrogen with 5 valence electrons. So this picture needs to have a total of 18 electrons in it. So I'm going to zoom in a little bit on this. Okay, so I need to have 18 electrons in this diagram. So I'll start by connecting everything. So that's 6 electrons, right? So I have 12 more to go in my picture. My hydrogen is done, right? I cannot have anything else with hydrogen. That 1 bond is it. So let's look at the oxygen. The oxygen next to the hydrogen would need to have 4 more electrons drawn in to complete its octet, because the oxygen and the nitrogen both need to have full, completed octets. The nitrogen would also need 4 more, and then this oxygen would need 6. But if we count right now for this, here's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So that's not going to work. So let's just take some electrons away. Why is my pen not working now? It's one of those days. Okay. Weird. So let's do a trial and error here. So let's go with that oxygen on the right with its completed octet. So we have in the picture right now, where's my pointer? Come back, laser. So here's 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so now we have all the electrons we can possibly get into this picture, but the nitrogen doesn't have a completed octet and it needs it. So what we can do here is we can swing a lone pair from this oxygen on the right in to make a double bond. So instead, we have this situation. Okay, so we didn't add any more electrons. We just moved them around to make, the nitrogen have a completed octet. Here's another example of a skeleton structure. You could probably determine this is a type of organic molecule. There's no organic chemistry in this course, so you don't have to worry about like memorizing those like functional groups from Regents Chem. So let's do a count here. So we have carbon, hydrogen, and oxygen. We have 1, 2, 3, 4, 5, 6 hydrogens with 1 valence electron apiece. We have 2 carbons with 4 valence electrons apiece, and we have 1 oxygen with 6 valence electrons. So our picture needs to have a total of 20 electrons in it. So I'm just going to start by connecting all of these atoms to one another using single bonds. Now I count to, what did I just do? I have, today's great. I have 2, 4, 6, 8, 10, 12, 14, 16 electrons drawn. So I only need 4 more electrons to complete my picture. Every hydrogen is done. Once hydrogen gets 1 line, it's done. The 2 carbons are done, right? Because they each have a completed octet. So the oxygen's sitting there like, oh, I only got 4. It needs 4 more electrons. Throw those in as lone pairs. And that takes care of the last 4 electrons, and that one is done. There are exceptions to the octet rule, dun dun dun. So when you're doing these drawings, you know that hydrogen gets 1 line and it's done. Carbon, nitrogen, oxygen, and fluorine always will obey the octet rule. So they must have 8, right? And it's easy to remember because carbon, nitrogen, oxygen, and fluorine are all right next to each other. A lot of times boron and beryllium will have fewer than 8. So you can be under, especially boron will show up. Any element in the second row can never exceed the octet rule, because if you're in the second row, you have 2 PELs, so you have you don't have the possibility of a D sublevel, right? The second PEL only has an S sublevel or a P sublevel, and an S sublevel only holds 2 electrons, a P sublevel only holds 6 electrons for a total of 8. You cannot exceed that. But once you get to the third period, the third PEL does have the potential to have a D sublevel. So any element in the third row or below will usually satisfy the octet rule, but can exceed the octet rule because there is the possibility of having a D sublevel. That element itself might not have a D sublevel in its base electron configuration, but it has the potential that it could, so you can go over 8. I show you now. The rule that you want to do is always, you follow the procedure we've been looking at, satisfy the octet first, but then if you have extra electrons left over and you have a central atom that can exceed the octet rule, so it's normally the central atom. So if it is a period 3, so you'd have to use a periodic table for this, a period 3 element or beyond, you can exceed the octet for it. So here's, if you go under for boron, I don't like this example, I just pretend that isn't there. So if we were doing boron trihydride and we were following our counting rules, boron, where am I? Boron is in group 13, so it has 3 valence electrons. and each hydrogen has 1 valence electron. So this picture that we're going to draw only is going to have 6. So when you put it together, the boron is your center, right? Hydrogen can never be a center. And then you put your hydrogens around and you connect them each with bonds. 2, 4, 6 electrons were just drawn. We're done. You do not need to complete the octet for boron. There's no more electrons left that can go into that picture. So it is done. Okay? Boron is really the only one you would see that goes under. Beryllium can, but beryllium's a metal, so it's usually going to bond ionically. And you wouldn't draw that like this. So really, just that one. Now, for the expanded octets, I'm going to take these molecules that are drawn here and show you how this works with the numbers we've been working with to show you the process of how we got there. So the first one is PCl5, phosphorus pentachloride. My alarm free period, okay. Phosphorus is in group 15, so it has 5 valence electrons. And then each chlorine, 5 chlorines with 7 valence electrons apiece because they're halogens. So 5 plus 35 is 40 electrons shown in this picture. So my center atom is going to be the phosphorus. And then I'm going to put these 5 chlorines around the perimeter. So cute. And then I start my connecting. Connect them to the center. So I just did 10 electrons, right? So 30 more electrons are left to draw in my picture. I'm going to satisfy the octet of my perimeter elements. So each chlorine needs to get 6 dots to complete their octets. 6 dots times 5 chlorines is 30 electrons. It's done. So this phosphorus in the center is showing 10 valence electrons. That is possible because phosphorus is in the 3rd row. The 3rd PEL can have a D sub level, so it's kind of invoking that D sub level. So that's an expanded octet on this phosphorus. This is a type of molecule you've never drawn before. We're going to talk about what that shape would be. For the center one, this is xenon difluoride, XeF2. So what's unique about this is xenon is a noble gas, and noble gases, you're like, wait, they don't bond with stuff. Sometimes they can. The larger ones can sometimes. They have lower ionization energies and they have low electronegativity values. They can, well, they have high, no, they don't have electronegativity values, but they can bond with stuff. So just be like, yes, they can. So we count. Xenon is a noble gas. It has 8 valence electrons. 2 fluorines are halogens. So that's 14 plus 8 is 22. So to build this one, I put the xenon in the middle because it's the singleton. I will put the fluorines on each side. I start by connecting them with bonds, so that's 4 electrons, so I have 18 left. I do the octet for my perimeter. Fluorine can only have an octet, no, nothing more, nothing less. So 6 electrons drawn on each of those fluorines is 12. That means I have 6 more electrons to go. Now, this xenon in the center already has 4 electrons. It's going to get 6 more. So instead of doing just 2 and 2, I'm going to do 3 sets of 2. Doesn't matter like where you put them. Don't put them right next to the bond, kind of put them at little angles the way that it's shown. But those are the extra 6 electrons. So that xenon can have, in this case, 2, 4, 6, 8, 10, it can have that expanded octet. Oh, sorry, you're seeing that leftovers will be added to the center. Here's 2 more examples. I'm going to draw them off to the side just again to show you the procedure. So that SF4 needs to have 34 electrons, 6 for the sulfur, 7 for each fluorine. So the sulfur goes in the center, fluorines all around. So you can see that tetrahedron shape getting built. There's 8 valence electrons. I need to complete my octet for each of the fluorines. So that's 6 times 4 is 24. Oops, count carefully. Count your dots carefully, please. So we have 32 electrons drawn, right? 8 times 4 is 32. We have 2 more electrons that have to go in. So I'm just going to throw them like hanging off the sodium, or I'm sorry, hanging off of the sulfur. The sulfur is in the 3rd row. It can expand its octet. And then this arsenic pentabromide, If you think about the periodic table, arsenic pentabromide, arsenic is right below phosphorus. We did PCl5 on the prior slide, right? Yeah, PCl5, arsenic is right below phosphorus, and then bromine is also a halogen. So same group, similar properties, you're going to get the same sort of situation, and you get the 40 electrons present. So you should be on the way to getting the hang of this Lewis structures. We're going to do more practice in class with you working on these. You need to just go through the motions to get these. You need to be able to identify elements that can either expand the octet and why, and elements, usually just boron, that would be okay being below the octet as well.